Let's consider how the small-scale properties are giving rise to larger-scale properties, our main theme for chemistry, right? At the small scale, we're going to have certain behaviors happening. And so we see that for solids, one of those small-scale behaviors is that there's not going to be a whole lot of motion. Now, I will want to emphasize that this is my animation skills in PowerPoint, so this isn't going to be completely authentic. This should be small vibration that we see happening with some random motion to it. Now that's even more important when we think about liquids. Liquids, we show them as if they're moving back and forth over and over again in the same path, and that's not at all accurate. They're moving around, but they're bouncing off and going in random directions, and they're staying pretty close together, almost as close together as in a solid. But liquids, when they become gases, have lots of space in between them and lots of movement. As long as you remember this is a limited quality animation, it gets the point across really well. And that point is that as we add heat energy, we end up having a lot more space in between our molecules and a lot more movement, especially in the transition from liquid to gas. And that's all because as you add more heat energy, they have more movement energy, more kinetic energy, and so they don't follow the same patterns so well. Now when we add some of that randomness, we're going to have big scale effects come from it. And let's take a look at an example of that. Okay, so now we see that we have our microscopic view for our solids, liquids, and gases. And we also have our macroscopic view, and we're going to fill in some details about these while considering the actual wider view of what we see for each of these flasks. Now for a solid, we have a little motion for the individual solid atoms. You can see that we're showing a decent amount of motion up here for the gases surrounding it, so that it matches up with our macroscopic view below. Now it's got a fixed shape, and that's because it's not moving very fast and they're staying stuck to its neighbor. There's going to be a surface, a spot where we can kind of just say, yep, that's where the solid ends and that's where the gas begins. It has a fixed surface to it, and it doesn't conform to the container. It can sit in a pile sitting at the bottom because it has a fixed shape and a surface. And there will be that pattern that gives rise to all those properties. Now with liquids, liquids don't have much pattern at all. Sometimes you hear people incorrectly tell you that there are patterns in liquids like water, but you got to remember that these are moving at some large fraction of the speed of light, and they're banging off of each other with a lot of energy. They're not going to have anything that persists for any length of time. There's not going to be any fixed shape within the flask. There's not going to be a hard surface, but there will still be a defined surface right here where you say the liquid ends here. Because they're all sticking to the other liquid molecules, there's a gas above it. It's going to conform to the container because it doesn't have any rigidity, and it's not going to have a pattern inside. Now with gases, all bets are off to some extent. There's no fixed shape for these. They're intermixed, in fact. Notice that our orange gas is mixed in with our blue gas now. They don't have a surface. They will conform to the container because they have no structure to them, and there is definitely no pattern at all for a gas. Those are going to be our three core states of matter we're going to talk about in chemistry. Now, in some other fields, you'll sometimes hear about things like plasmas. Plasmas are often considered to be a state of matter, but they're not going to be chemically important, especially not at the chemistry 1 level. So we won't be discussing plasmas in this course, at least not at this time.